Hello and welcome everyone to the 20th World Congress of Psychophysiology. This session is about electrophysiology and long-term effects of malnutrition. My name is Fuleah Razzaq and I am chairing this session. The presenter of this session are Dr. Jorge Bosh, Dr. Anna Calzada, and myself. The focus of today's session is early childhood malnutrition. The speakers will share their work and what kind of tools and techniques they are using to analyze the effects of malnutrition. The World Health Organization categorizes malnutrition in three different forms: stunting, overweight, and wasting. Stunting is the most severe form of malnutrition that has both physical and cognitive effects. All the works presented in this session target stunting. According to 2017 Joint Child Malnutrition estimates by WHO, UNICEF, and World Bank, there are 155 million stunted children worldwide. The percentage of stunted children under 5 worldwide is given in this map, and there are 22.9% children stunted globally, and these are the children who are malnourished under the age of 5. And there are 5 sub-regions in the map you can see that exceed the 30% limit, which includes Africa, Southeastern Asia. Barbados is an island in Caribbean. All the speakers in this talk are working on a unique dataset of Barbados nutrition study. It's a longitudinal data for more than 45 years. The lead of this study is Professor Janina Geller, and the first wave of data was captured in 1978. The dataset includes children who had normal birth weight but suffered protein energy malnutrition in first year of their lives. Right after the diagnosis, these children were submitted to a national intervention program, and they were under that program until the age of 12. This program ensured that no child in this group had further episodes of malnutrition, which makes this dataset very unique as it has children with a single episode in first year of their lives. These children were then matched to healthy controls and followed throughout their lives, and different waves of data was collected. Also, the second generation or the offsprings of the children, we also have data for those subjects. And the data include different cognitive, psychological, and brain measurements, as well as regular health and blood checkup. And it has 7 waves, and further details of different tests and variables, you can find them in individual talks. So let's get started. The first talk is by Dr. Jorge Bosh. He is a computer scientist with a PhD in health sciences. He started his career at the Cuban Neuroscience Center and currently working at the McGill Center for Integrative Neuroscience, Montreal Neurological Institute. He developed methods for EEG analysis for source localization and connectivity. His work include quantitative EEG and discovery of biomarkers for neurodevelopmental disorders. Let's hear from him.
Hello, this is a presentation I am going to make for the 20th World Congress of Psychophysiology, IOP 2021. First, I want to thank Dr. Fuleah, Razzaq, and Pedro Valdez for inviting me to participate in this symposium. My presentation is entitled Quantitative Eeg Follow-up in the Longitudinal Barbados Malnutrition Study 45 years later. As you can see here, authors come from different institutions, different countries. It's a multinational study participating McGill University, the University of Electronic Science and Technology of China, the Cuban Neuroscience Center, the University of Montreal, Brain Research Laboratories at the New York University, and the Massachusetts General Hospital for Children in Boston. As an introduction, let's say that malnutrition is a persistent problem worldwide that affects around 23% of children in developing countries, according to UNICEF 2017. The most prevalent form of malnutrition is protein energy malnutrition, PEN, which is defined as insufficient protein consumption and or caloric intake. PEN affects an estimated of 155 million children globally, even in industrialized nations such as the United States, according to the Global Health Observatory 2016. And nearly half of the deaths of children under the age of 5 are attributable to undernutrition. Regarding PEN, Graham McGregor et al. Found that PEN can have long-term effect on cognition and behavior, as well as on brain development. Early exposure to PEN during a critical period of brain development, for example, from the second trimester to pregnancy to 2 years old, have been shown to produce permanent brain-related changes. In this work, we are going to present the quantitative EEG analysis of a 45-year follow-up to a cohort of children in Barbados who suffered pain during the first year of life. The Barbados malnutrition study started around 1975. Barbados is a small island in the Caribbean. It was a study performed by Dr. Janina Galler in collaboration with the Ministry of Health of Barbados and Dr. Roy Joan Leslie Pritchett, who provided the EEG hardware and performed the EEG analysis at that time. The participants of this study consisted in children that were born between 1967 and 1972 in Barbados, who were diagnosed with pain in the first year of life. So these children suffered malnutrition during the first year of life. The grade 2 or grade 3 pain episode, but it was only one episode that they suffered during the first year. After that, these children were admitted at the hospital, Queen Elizabeth Hospital in Barbados, and they were enrolled in a national program, of nutrition program in Barbados until the age of 12 years, and they never suffered malnutrition again. So they only had this episode once in their life, and it was during the first year of life. This study included many different types of measurement, but in specific, the EEGs were recorded in 1977 and 1978 by trained staff at Barbados Nutrition Center when the children were around between 5 and 11 years old. A matched healthy control group of classmates were selected who met the same inclusion criteria as the pain group but lacked a history of malnutrition. The EEG experts were blind to the children's history of malnutrition. In 2018, the Cuban Neuroscience Center performed a new EEG acquisition from part of this subject of the original sample. The original sample that was 129 children, they were able to recover or register again, to contact again 43 persons with pain diagnosis and 51 control persons. So from the original cohort, from the original study. However, because of the long time and because of that, there many recordings were damaged. Only 23 pain and 30 control recorded in 2018 were part of the sample in 1978. So for this small subset, we have the 2 recordings in 1978 and 2018. The new sample was compared with 46 pain children and 62 control classmates that were recorded in 1978. In both studies, the EEG recordings consisting in eye-closed resting state, 19 channels of the 1020 International Positioning Electrode System. The sampling rate in 1978 was 100 Hertz. In 2018 was 200 Hertz. The two equipments were different. 24 epochs of artifact-free of 2.56 second duration were manually selected by the EEG expert for the analysis in all subjects, and the EEG experts were blind to the children's history of malnutrition. The Quantitative Eeg Methodology developed that CENEURO was used. This table summarizes the participants in this study: 46, 1978, 43, 2018, 62, and 51. And common to the both study were 23 pain, 30 control, 128 in 1978, and 94 in 2018. So what is the quantitative tomographic EEG analysis as we perform? So we have here recordings coming from two different systems in two very different epochs in time, one to children and one to adults. The equipment in 1978, we collected 24 epochs artifact-free, 19 channels of the 1020 system. It was acquired with the data system provided by the BRL, Brain Research Laboratory. At that time, that equipment had a sampling rate of, or frequency rate of 100 Hertz. And the epochs that we selected for the analysis were 2.56 seconds, which are 256 points in time. In the equipment 2018, we had again 24 epochs artifact-free, manually selected by EEG experts. We also analyzed 19 channels of the 1020 system, and we have this EEG were acquired with the Mediation from Neuronic Cuban equipment. The sampling rate was 200 Hertz, and we obtained the same epoch of 2.56 seconds with 512 points, and this is to warranty. So the 2.56 second warranty that at the end we can have for both of them, for both of the equipment, we can have a frequency range with a sampling resolution of 0.39 Hertz, and we will analyze from 0.39 Hertz to 11.11 Hertz. Which was the processing that we did with? The artifact-free epochs were first average reference, and then we apply the global scale factor. The global scale factor is the factor that we defined at the Cuban Neuroscience Center in 1994, and this factor is thought for harmonizing recordings that come from different devices and from different subjects. For example, the global scale factor is correcting the EEG by baseline that make the recording comparable after that correction. This factor is calculated individually for each individual, for each recording, and it is this factor accounts for variability in the EEG that is not due to neurophysiological factors, like, for example, differences in the amplifiers of the equipment, differences in the impedance, for example, in different school fitness or other technical factors that affect the amplitude of the EEG spectra, but they are not really related to neurophysiological matter. After we apply this factor allows to have more comparable spectra for the statistical analysis. Then we send this EEG in the time domain, we send to the quantitative EEG analysis. So these are the free EEG epochs, the free artifact-free EEG epochs. We apply the Fourier transform. So we convert this to the frequency domain, and we obtain the spectra for each of these. So we obtain for each channel the spectra, and we also calculate the cross-spectral matrices. Then we apply here the Vareta inverse solution method, and we calculate the estimate of the spectra at the sources, at the EEG sources. So we have a spectra at the scalp, and we have spectra at the sources. And with this, we compare this spectra with the spectra coming from the Cuban normative data. So we obtain set probability measurements that are compared against the Cuban normative project that provided us the mean and the standard deviation of the normal population according to the age. So these regression equations are depending on age, and with this we calculate a measurement that is a deviation against normality, so the deviation from normality. The advantage of having this measurement is that by this we correct the effect of the age on the EEG. We know that the age depends on the age. There are variances, changes in the EEG due to the age, and when correcting by the typical spectra at the age of the subject, then this is age-free. This measurement is age-free and is expressing deviation from the normality. So after this procedure, we obtain the EEG spectra at the 19 channels when we do at the scalp, and at the 3,244 sources when we do at the sources. And we obtain raw and Z-score in the previous mentioned frequency range, 0.39 to 19 Hertz every 0.39 Hertz. In this work, we are going to focus only in the analysis of the sources, because the analysis at the scalp don't provide a localization on the generators of the EEG differences. So this is the general methodology of this work. We have the 46 pain in the first study, 62 control in the pre-study. We have the 43 pain post in the post-study, and 51. So this is the voltage in time. We send them to the quantitative EEG analysis that I already explained. And from this, we obtain the Z-scores at the source spectra. So we have here the Z-scores for the pain pre, for the control pre, from the pain post, and the control post group. So we have two groups and two studies, and we want to compare them. For this, we use the linear mixed effect model. And the specific model that we use here is that we include the group, we include the study, and we include the interaction between the groups and the study. And we consider also the random effect of the subject, because as we have a partially dependent sample, we have 23 subjects in pain and 30 subjects in control that are dependent because we have the two studies, then we include this information as a random factor in our model. The groups are pain and control. The study are pre, which is 1977-78, and the post, that is 2018. And the subjects account for repeated measurement, and this is the interaction between group and study. For this, we analyze the following contrast. We calculate the difference post minus pre in control. That is the difference, so it's the contrast of the maturation, express the maturation of the control group, the post minus pre in the pain group, that is the maturation in the pain group. We find the differences between the two groups in the childhood, so in the pre-study. We find the differences between the two groups in the post-study, in the adult study, and we find finally the maturation, the difference of maturation between the two groups, that in this case consists in finding the difference of pain minus control, but we correct both studies by the pre-study. So we correct we subtract the post minus pre, and with this contrast, we are eliminating the influence of the starting point in the two studies. After that, so we have this contrast, but we need to correct our results by the high number of variables that we are analyzing, a high number of statistical comparisons with a relatively small number of subjects. So we use the permutation test to find the threshold of corrected threshold of significance by doing a high number of random repetition of the linear effect model and obtaining the corrected threshold. And after that, we finally have the significant contrast. So we have the contrast, but corrected by the proper level of threshold. To be sure that we had the use of the Cuban normative database did not affect our results, since we are applying this to Barbados children. What we did was we calculated the fixed spectra of the control group in the first study. So this is the C spectra of the control group in the childhood. And what we found here is that effectively the control group is inside the normal range. So for example, we have here that the majority of almost all are inside the 2 standard deviation. There are only very few outliers in the group, so in isolated electrodes, but in general, the great majority of all the recordings are inside the normal range. So this was a good result to assess that using the Cuban normative database is valid to compare these Barbados children. So the first result we analyze is the maturation of the control group. So it's the difference between the pre and the post study in the control group. And what we found here is that we didn't find any significant difference in the delta, theta, or low alpha frequency bands for the control group, which is a positive result to say that the control group continue to be a normal group after 45 years of age. In this case, we have calculated the statistical analysis with 2 thresholds. So we use a threshold at 0.05 and the threshold at 0.01 to be more strict, because since we are having small sample, we want to concentrate only in those differences that are very very high between the two groups or between the two studies. And what we see here is that there is in the high alpha, in the adulthood, there is more activity in these frontocentral areas, and there was a little higher activity in the left hemisphere, in the occipital, in the control, in the pre-study. So this is indicating that there was more activity in the pre, and this is indicating, the colors are indicating that there is more activity in the post. But the important thing is that there are not differences in this band that express more pathological activity. When we look at the pain, the maturation of the pain group, we found that there was more activity in delta in the pre-study. So remember, here we are subtracting post minus pre, so negative mean that pre has higher, and there was also higher activity in the low alpha in the post study. So in the adulthood, they have more activity in low alpha. This here in theta shows more or less the same behavior that low alpha, but this is not significant at the level of P 0.01. It's only significant at 0.05, and here also is significant 0.05, and this also is significant at 0.05. So the significant changes at P equals 0.05 in the pain group are related to excess of delta and the effect of low alpha band in the childhood regarding adulthood. A slow delta rings decrease with age, moving towards normative values. So this can be an explanation that in the adulthood, this delta rings decrease. This decrease means that they move towards normative value. This slow activity coincides with attentional and behavioral problems during the childhood, which might be compensating with age. And the modulation of alpha activity was incomplete, evident in the low alpha band that shows more activity than in the childhood. And this contrasts with the increase of the high alpha band for the control group, which may mean that there was an incomplete modulation for the pain group and maybe a shift of the alpha peak to a slower band. So instead of the alpha peak in the control group was more in the high alpha, and for the pain group it was more in the low alpha band. The child dysfunction. This is the comparison between the control and the pain group in the childhood, so in the first study when they were a child in the recording of 1978. Is control this is pain minus control. So what we found here is that there is a higher activity in delta in frontocentral brain area. There was a difference in the high alpha in large area of temporal, parietal, and frontal of the right hemisphere, and small one in the high alpha in the left hemisphere. And in beta, there was a decrease of activity in the beta band in the pain group. So here are the results. The activity, the delta activity was more pronounced in frontocentral areas. The increase of I alpha, mainly prefrontal areas. The decrease of beta. This difference between the groups in the childhood has already been observed in previous group works by our group with a bigger sample and in both groups with different techniques. So in this case, using QEET based Vareta and QEET based on BC Vareta. These are two different papers with different samples that showed more or less the same result. And the importance of this finding is that even that we have here a smaller sample, the results are consistent. So it makes more confident. It makes us more confident on that if we are analyzing a smaller sample, but we are retaining the main characteristic of the group in this analysis. So in the adulthood, so the study in the adulthood at the recording 2018 show that control group, the pain group has a higher low alpha in frontal areas and has a lower high alpha in temporal and parietal areas. So this is extended bilaterally, but in the two hemispheres. In the occipital, it's more extended, but only this part was significant at P0.01. And this increase of beta in superior temporal and parietal. The differences after 40 years, there are no differences in delta and theta band. Is what we found, that there are no differences in delta and theta band 40 years after, which means that as we said before, the alpha, the delta activity normalized with the age in the pain group. The excess of low alpha and the effect of high alpha in pain, as I already said, may indicate different patterns of maturation than pain control group and a shift of the alpha peak toward the slower difference than control. So as I said, that the alpha rhythm has a peak for control in adulthood around 10 Hz, while at the pain is around 7.8 to 8.2 Hz. These differences, however, all taking all into account, may indicate that there is a higher degree of maturation in the pain group, but at the same time, the maturation was not as good as in the control group. So still that they maturate, so they have they show a maturation, an improvement in their EEG activity. This is still different from what we observe in the control group. Finally, the last contrast that we calculated is the maturational contrast. That is the difference between the two groups at the post study, but removing, so correcting by the first study, so removing the pre-study. This is like putting all the subjects in the same baseline. So here what we see are the differences between the two groups, but which are not due to the different initial state they have. And what we see here is that this difference, so the differences appear in the same band that before in the previous contrast, In this case, is the areas that are significant at P01 is smaller, it's more concentrated in low alpha in the prefrontal lobe. The differences in high alpha are wider, and they take almost the whole temporal lobe. They take a big part of the parietal and part of the occipital and part of the frontal. So this is wider than before. And the differences in beta design are appear bilateral in the whole occipital, taking part of the temporal and taking part of the parietal, almost the full parietal in the two lobes. So the difference that we observed before in the previous contracts are more highlighted in this, are more bigger here, showing the difference in the maturation of the developing of the two groups after from the childhood to adult. So this contrast reinforced the results from the previous one. The fact highlights that the two groups developed differently independently of the baseline. The difference appear at the same frequencies in the low alpha, as I already explained, at the high alpha and the beta band. As discussed before, these changes emphasize the slowest maturation of the pen group independently of their initial status. And several authors have reported that the increment of beta activity is related to cognitive impairment and premature aging in this group. So after all, what this analysis is showing is that suffering one single episode of pain during the first year of life resulted in a developmental delay of the brain's normal rhythm, both at school age and adult. This developmental delay manifests itself as a slower shift to higher frequencies of the sources of alpha rings in pain impacted children, a pattern that we call EEG stunting. In the adulthood, the increment of beta rings suggests concomitant premature aging or cognitive decline. In our opinion, the quantitative electroencephalographic tomography is therefore an inexpensive, valid, and objective measure to identify the long life effect of early malnutrition on the brain. Thank you very much.
Thank you, Dr. Jorge, for such a nice talk. Now, our next speaker is Dr. Ana Calzada. She is Head of Clinical Neurophysiology Department at Cuban Center for Neuroscience. She is a medical doctor with specialization in clinical neurophysiology. She also has a PhD in medical sciences. Her talk today is on qualitative EEG, and now I would like to invite her to give her talk. Thank you.
Hello, everyone. Today, the topic of my talk is Qualitative EEG measures to discriminate long-term effects of malnutrition. The electroencephalogram is the most used neuroimaging technique to identify the effects of early infants on the brain, including protein energy malnutrition. The EEG analysis can be done either using qualitative or quantitative methods, with each approach focusing on different properties and features of the EEG recordings. Longitudinal studies constitute the best methodological approach to study how malnutrition can influence brain function. Accordingly, we report the qualitative and semi-quantitative analysis of EEG's recordings done in 1978 and 40 years later, in a subsample of the first generation of participants from the Barbados nutrition study. We used visual inspection of EEG recordings by two experts to identify abnormalities and score the individual items of the one semi-quantitative scale. Grand total EEG, which has been employed to study EEG abnormalities in dementia and Parkinson's disorder. The aim of the present study was to determine whether visual and EEG semi-quantitative analysis using a latent variable can shed light about the long-term effects of childhood malnutrition. The current study was conducted in Barbados, a Caribbean country whose population is 280,000 at present. Study participants were born between 1967 to 1972 and had a history of childhood malnutrition. The first EEG dataset of the original BNS sample was recorded between 1977 to 1978, N equals 258, when the subjects were between 5 to 12 years old, and 108 recordings were used for subsequent analysis. EEG was recorded again 40 years later in 2018, N equals 97, when the participants were between 45 to 51 years, with 97 valid EEG recordings. Mean age was 48.2 years, SD 2.14. For comparison between the EEG at the two recording times, we selected only participants who had EEG recordings at both ages, N equals 54, subdivided into two groups. PEM and control matched in age, 48.7, SD equals 2.7. The EEG recordings were evaluated independently by two clinical neurophysiologists from the Cuban Neuroscience Center, who were blind to the participants' malnutrition history, using the standard criteria from the International Federation of Clinical Neurophysiology. To carry out more sensitive analysis of the EEG visual inspection data, we devised a linker type scale based on an ordinal grading scale of perceived abnormality, modified from Jonkman, 1989, and Derweird and others, 1990. This semi-quantitative scale summarized the EEG findings of the EEGs previously found by visual inspection, where 0 is the absence of abnormality and 1, 2, or 3 represent different severity levels. To statistical analysis, chain square contingency tables were used to analyze the statistical significance of the frequency of abnormalities detected by visual inspection of the EEG recordings of both groups in 1978 and 2018. The first step to analyze the results in the GTE scale was to obtain the reliability of the items using the item response theory paradigm. The second step was to integrate the latent variable in a multivariate item response theory approach, testing the differences between groups with a multi-dimensional item response model. Visual inspection of the EEG recordings demonstrated a preponderance of abnormalities in the PEM group in comparison with the control in both 1978 and 2018 datasets, with more abnormal findings reported in 2018 than in 1978. Multivariate item response theory results. Not that focal abnormality and diffuse slow activity were the most significant items to discriminate between groups. F1 is above 0.7. Comparison between groups 1978 and 2018. For the comparison of the two times, we calculated the mean and standard deviations of the F1 scores and for the 5 items employed in the final analysis, first intergroups and later intergroups in each time point. Comparison intergroup with the scores by items in 2 times. Blue indicated the 1978 recordings and orange the 2018. PM all the items have higher values in 1978. Controls have also higher values in 78 with the exception of diffuse slow activity which incremented in 2018. Distribution of the mean and standard deviation of the groups PEM and control in the 2 years. Here, in the 2 times, PEM had higher values than controls systematically. Item analysis for the subsample N equals 54 with EEG at both 1978 and 2018. The focal abnormality item was the most significant predictor, followed by diffuse slow activity and paroxysmal activity. The GTE scale readouts were more informative when an item analysis was employed than using a global score. The multivariate items response theory approach used in this report was found to be a robust and reliable method to identify the differences between nutrition groups in childhood and middle adulthood. At both time points, the persistence of focal abnormalities appeared to be the most discriminant item supporting the differences between groups. The persistence of slow focal abnormalities could be representative of the impact of early childhood malnutrition on adult brain function. Diffuse slow activity was other important item that showed significant difference between both groups. This type of EEG abnormality is related with global cerebral dysfunction. Our finding could be reflects the irreversible neurological consequences of early childhood malnutrition. The GTE scale readouts were more informative when an item analysis was employed than using a global score. The multivariate item response theory approach used in this report was found to be a robust and reliable method to identify the differences between nutrition groups in childhood and in middle adulthood. At both time points, the persistence of focal abnormalities appeared to be the most discriminant item supporting the differences between groups. The persistence of slow focal abnormalities could be representative of the impact of early childhood malnutrition on adult brain function. Diffuse slow activity was other important item that showed significant difference between both groups. This type of EEG abnormality is related with global cerebral dysfunction. Our finding could be reflects the irreversible neurological consequences of early childhood malnutrition.
Thank you, Dr. Anna. And now the final talk of today's session is from me, and I would like to get started with it. First, I would like to start with a little introduction about myself. I'm basically a computer scientist with a specialization in biomedical imaging and neuroinformatics. I have a PhD in computer science from Deakin University, Australia, and now I'm working as a postdoc in UESTC, China, in a neuroinformatics lab for almost 3 years. My research interests are causal inference, statistical inference, hypothesis testing, data science, machine learning. And the topic of my talk today is early malnutrition induced premature cognitive aging is causally mediated by school-age brain states. As you already know about Barbados nutritional study, so I would not bore you with the details, but I would give you a brief introduction of what data I am using for this analysis. So I am using data from two waves from 1978, that is the childhood data, and then from wave 7, that was in 2018. And the variable I am using are EEG and two variants of EEG, the quantitative EEG that was Dr. Bosh's talk, and the qualitative EEG that was Dr. Anna's talk, and also soft neurological science, as well as some age appropriate cognitive variables like WISC for children and MoCA for adults. Then I'm using age, gender, and childhood socioeconomic status as confounding variables. This table shows the summary of the sample. So I'm using the common subjects, in which 23 are malnourished individuals and 29 controls, and both groups have 13 male. And then the WISC full IQ scores and MoCA total scores. You can see the mean and standard deviation, and also the standard mean difference, which is significantly different between both groups. So this is the processing pipeline for this analysis, and we have already established what kind of measurements or recorded data we have. So this is the phase we currently discussed. The EEG is then further processed using QEEGT and GTE, that is qualitative and quantitative EEGs, and then there are multiple stages that this data will pass, and I will explain each of them individually, and then finally we'll test some mediation hypothesis, and we will conclude on the results. So this is the main model that we want to test for this analysis. The model, this model is actually drawn from the hypothesis that malnutrition causes changes in structural and functional aspects of the brain, and that cause cognitive changes. So what we want to see that this is the group malnutrition, our controls, and then malnutrition does something to brain, and then brain state, and those changes are mm, further reflected in cognitive scores. And this is the model we want to test, but we don't want to just test the associations. We want to test the model, the causal effects of these variables. Also, for this model, brain state is a latent variable that is measured by EEG, GTE, and so qualitative and quantitative EEG and soft neurological signs. And the cognition is measured by age-appropriate test scores, which I already explained that we have used WISC and MoCA. And also we are not just interested in a time point specific model, but we want to see this or test this hypothesis in longitudinal sense, and I will explain that further in later slides. So the first step after the data acquisition was to process the EEG, the qualitative and quantitative EEG, and you already know a whole lot about it, so I'll just show you some results. So this is the average power spectral density between both groups and both waves. So this is x-axis is the frequency and y-axis is the power. Each line represents a channel or an electrode, EEG electrode, and we averaged it over subjects and or individuals. So these are PEM and these are controls. So you can see the difference between, it's clear that the spectra between PEM and control is very different. The spectra for PEM is quite noisy looking in comparison to control, and whereas if you go in adult life, you can see that the alpha peak is shifted and it shows poor electric maturation, and you see that the PEM has alpha on low alpha side, whereas for control it's on higher alpha side. So even without any kind of analysis, we can see the difference just in EEG, and this matches with the previous talks. So the first major step was to deal with the high dimensionality of data, because we had only 53 subjects and we have more than 1,000 variables, and most of traditional algorithms fail when you have more variables and less samples. So the very first thing we needed to deal with to actually test the hypothesis was to reduce the dimensionality without losing too much information. So I'm going to dig deeper into that one. Okay, so the very first step was to do screening based on associations, as we are going towards the causal analysis. So we want to only retain the variables who have some kind of association with the outcome, which is cognition. And because if there is no association between the mediator and outcome, uh, there is no chance there will be any causation. So we want to exclude as many variables as we can to reduce the dimensionality on only keeping the most relevant variables. For that, what we did, we used a global test. It works as multiple regression, but it works with high dimensional data when you have more variables and less number of samples. What it does, it uh, run multiple tests and check different combinations of variables and run multiple regressions, and it gives you an overall value for your regression as well as individual p-value for each variable, and we use those p-values to either select a variable for to be included in the further analysis or reject a variable. We tested, we ran 9 different global tests, uh, and the regression equation was this. So we had y, which was our cognitive scores, age-appropriate cognitive scores. Then we have group, PAM or control, and then we have our brain measurements, which was EEG, GT, and soft neurological sign. And the 9 regressions were based on different time points. So we tested WISC full IQ scores against the 1978 neuroimaging variables. Then we tested MoCA total score against 2018 neuroimaging variables, and also MoCA total scores against 1978 neuroimaging. So we tested these 3 different regression models on 3 different subsamples. The samples were all subjects, then PEM only and control only. We wanted to try and include as many variables as we can and not lose any associations or information, and just wanted to discard variables that we are certain of that they are not contributing between the group differences. So after getting the p-values from all these 9 regressions, we selected the we adjusted those p-values using home correction, and then we selected at alpha 0.01 level. We selected any variable that was significant in any of 9 regression, and we rejected all the variables that were never significant in any one of those. And here is just a summary of how the result changed when we used all the variables and when we use just a subset of the most relevant variables. So this before regression, these are the overall p-values for these regressions. So you can see that the significance level is improving. So for all subjects, it's definitely more significant now. For this one, it was not significant, but after discarding extra variables, it becomes more significant. But definitely, you can also see that there are certain regressions which didn't improve and stayed pretty much same. But this was not the goal. The goal was to retain only the most relevant variable, which we achieved using this process. So here are the results from the EEG after screening. These are the significant p-values, and this figure shows the variables which got selected from the EEG. These are the individual p-values, and we plotted them against different electrodes and different frequencies. This is actually 1 minus p-value for the visibility purposes. This threshold line, this is the significance level, which is 0.01, and anything this shaded red area above that is actually the variables that got selected, and we will be using them for further analysis. And you can see what we are getting actually is lots of alpha and lots of electrodes. You can see here, and then on the second thing we are getting is theta. That is also in I think roughly 11 electrodes. We have theta as well, and we also have some activity in delta and beta band, but the proportion is minor. So this is what after discarding the irrelevant variables, these are the variables we are moving forward from EEG. And in terms of dimensionality reduction, we were able to reduce out of 912, we were able to go to 145 variables from quantitative EEG, and for soft neurological science, it was 7 out of 16, and for GT, it was 5 out of 10 variables. So the next step in the pipeline is to apply principal component analysis. on the selected variables. The reason to do this step was that we wanted to retain the maximum variance with even a lower number of dimensions or variables, and that's why we transform the original variable into principal components. This PCA was used as a common step between the dimensionality reduction phase and the latent variable modeling, and I'll explain you in a while that why is that. So as I already told you that PCA was implemented as an initial step for latent variable modeling. So the variance that we retained, or the number of principal components that we selected, was not actually based on the total variance, but it was based on the model fit indices for the SEM latent variable modeling. And here are the results for 1978 EEG, and these are the principal components. We used first two principal components for 1978 quantitative EEG, and these are the result. These are the loadings from PCA. It's the sum absolute of both components, and we wanted to fit them in single figure. That's why we discarded the sign and added them up to show in a plot that what we actually getting in first two components. And you can again see definitely the power is a bit less. It's not as much as all the data, because we are only explaining 38% of variance here, but you can see that there are lots of activity and alpha, and the second most active band is theta, like here. So the results were similar to the p-value plot, and initially we retained 80% variance principal components, and then we tested different models for the latent variable modeling using SAM, and we decided to retain a certain number of components based on the model fit indices, and which model was doing better. And I'll show you that in the next slide. But eventually what we were able to retain was this much variance from each variable. So EG 78 was 38%, EG 2018 was 49%, GT was 48 and then 49, and sophomological science was 45 and 72%. With this step, our dimensionality reduction phase was finished, and this was kind of pre-processing and cleaning of data. And now we actually moved on to constructing our latent variable for brain state and for cognition. So we passed all the data that we have so far, all these variables, into a SAM model, and we reconstructed our univariate brain state and cognition. So latent variable modeling comes under structural equation modeling, and it's a model-based technique. What it essentially does is it involves a factor analysis and multiple regression. It does some path analysis, and we hypothesized a model first, and then we run this hypothesized model against the data and see how much it matches the collected data. It's also known as the measurement model. So the variables in squares are the measured instruments or measured variables, and then they are loaded onto these latent variables. So we wanted to construct four different variables, two from childhood and two from adult life, and brain states and cognition. We kept them all in a single model so that the association or the correlation between these latent variables is also retained, and we didn't want to destroy any kind of information or association that the data here has. And the number of principal components are that we eventually use to reconstruct these latent variables is here, and this was based on the model fit indices. The best model fit indices we got was for this particular one, where the comparative fit index was 0.952, the lowest index was 0.942, and the root mean square error was 0.041, with the 90% confidence interval between 0 to 0 mm, 0.081, and the standard root mean square residual was 0.093. So we used a Lavaan package from R to implement this, and we constructed these four variables to finally test the hypothesis that we wanted to test. Brings us to the last stage of our processing pipeline, where we tested different mediation models for our hypothesis and also applied the sensitivity analysis to check for the robustness of our hypothesis. So now I will briefly explain the theory of causal mediation analysis for the better understanding of the result. So this is the mediation model that we want to test, and our X or exposure is PEM, and our outcome is cognition, and we are interested in this indirect path which goes via brain state. So PEM is affecting brain state, and then brain state is affecting cognition, and then of course there is a direct path as well. So we want to know what are the direct causal link between these two variables, and what is the causal mechanism that is going through the brain state. And for that we are using a counterfactual based analysis, because if you want to go for causality and not association, the one thing you need to make sure is do a completely randomized trial, which is not possible for such cases, because we cannot randomly assign people to suffer from malnutrition. That is wrong on so many levels. So for such studies, for such clinical studies, what we does that we want to construct a causal effect in a case where, for example, the exposure here is binary, so it's either 1 or 0. You have malnourishment or you don't have malnourishment. So what we want to see is that any individual, the outcome for an individual when he or she is malnourished, if it's not equal to the outcome for the same individual when he or she is not malnourished, and if these two outcomes are different, then we will say that there is a causal effect. So the main theme is that we want to measure the two outcomes for the same individuals, and we want to see that if they are different, and then if they are different, then we can say that X is actually causing Y. But of course, we cannot observe both outcomes for the same individual. So either an individual is malnourished or he is not, but we cannot have both outcomes for the same individual. And for that, we apply different kind of approaches to reconstruct that other outcome, which is known as counterfactual outcome or potential outcome. So the outcome that we observe is the actual outcome, and then there is another outcome that is uh, counterfactual or the possible outcome, and we try to reconstruct it. And there are many different approaches and techniques to do that, and you do some probability weighting, and you assign different kind of weights to create a pseudo random population, rather than because we cannot have a completely random uh, trial. So we create a pseudo random population and then try to construct these effects, and there are other such things that we do. But the goal is to construct a population of same subjects, uh, where we can compare the effects when we have PEM and when we don't have PEM. So sensitivity analysis is used to see how robust your ACME estimates are. ACME is average causal mediation effect, and you want to definitely know your estimates for direct effect and indirect effect, how robust they are, how stable they are, and how much they are polluted due to any unknown or unmeasured data, which is confounding those results. So we are using the mediation package in R to run these analysis, and this is the sensitivity as analysis is also from the same package, and this is the plots that it gives you to show the results. So for x-axis you have the sensitivity parameter. It's a correlation term, And what it does, it measures the correlation between the two regressions, the exposure mediator regression and the mediator outcome regression. And if those error terms are correlated, then the one possible reason can be that there is some third unknown or unmeasured confounding factor that is affecting or causing some kind of effect on both of the variables at the same time. That's why their error terms are similar. So what it does, it creates a simulated data where it correlate the error terms and then try to estimate the mediation effect. And then this is the this plot is result of that simulation. So this dotted line is the initial ACME estimate that is coming from your data, and on x-axis the row is varying from -1 to +1. And you can see that the sensitivity parameter is touching the 0 on y-axis at this value. So this will be somewhere point positive 0.8 or 0.9. So what this plot is telling us that for any value of sensitivity parameter rho under 0.8, your ACME estimate will hold its direction, which was negative initially, and will not become 0. So if you have a -1 correlation, even then you have such a high confounding, but that is in opposite direction. It will not change any kind of anything in your ACME estimate, and your ACME estimate will hold. And for other values, your ACME estimate can increase or decrease, but it will still be there until or unless you have a positive correlation of 0.08 or 0.9. So you have such a huge confounding that it's almost completely affecting both variables. Only then these results will be null and void. So it's safe to say that there is some kind of causality between these variables. And we use the same kind of plots to test the hypothesis that we want to test for our analysis. So we constructed these 4 causal DAGs to check for the long-term and short-term effect of PEM on cognition. So the first column is our point estimates, and the second column is longitudinal in the sense that it is using data from both time points. And the first estimate is purely for 1978 because the brain state is from 1978, and also the cognition is 1978. So what we are testing for is that in childhood, how the brain state is affecting the causal of is mediating the causal effects of PEM on the cognition in childhood. And the second point estimate is for 2018, and here we are looking for that how the PEM is affecting on the adult cognition, and how that effect is mediated with the adult brain state. So these are both the time specific hypothesis, and we are taking the mediator from the same time point and also testing that how the effect of malnutrition in the childhood is mediated by the brain state of childhood, and how the effect of PEM on the adult cognition is mediated by adult brain state. Then these 2-point estimates are for longitudinal data. Here we are testing for that how the adulthood cognition is mediated by the childhood brain state. So how much of the effects in the later life are actually coming from the structural or functional aspect that change in the early life, and how much we can map between these two. And this one is we are using two mediator model. So we are checking for that how much so the main path is the adult mediator, how much adult mediator adult brain state is mediating the adult cognition. But then we are including the childhood brain state as second mediator, and we are saying that this is a common variable that is affecting both the main mediator and also the main outcome. So the childhood brain state is there, that is affecting the later life brain state, of course, and also the later life cognition, and then also the adult brain state is affecting the cognition. So we want to test these four different hypotheses to establish how much the uh, malnutrition affecting the structural and functional aspects of brain, and that is affecting the quality of life and the cognition of the individual. And all are these effects just in a specific time, or all these effects can be mapped over the year and throughout the life. And of course, for all these models, we have included age, gender, and childhood socioeconomic status as uh, pre-treatment confounding variables. So these are the results from our time-specific models. So for the first model that we have tested was the brain state 78 with the outcome as cognition 78, and what we found that the ACME, that is average causal mediation effect, was negative zero point 0.6, and the direct effect between the PEM and the cognition was somewhere negative zero point 0.3. But only ECME was significant, not the direct effect. And this is the sensitivity plot for this ECME estimate, and to see for or check for its robustness, that the plot is shows uh, quite stable estimates that for a larger range of row, the acme is there and it's non-zero and it's in same direction. So that tells us that actually PAM, the effects of PAM can be mediated by the changes in the brain. And then this is the model for the adult life. Again, we are testing the same kind of model, but rather than in the childhood, the time is 45 years later after the episode of PAM. And here you can see that the ACME estimate is a little lesser than this one, so the value is negative zero point 0.4 here, and the direct effect is nearly zero, and also it was not significant. And the sensitivity plot is um, a little less robust than this one, but it's still quite stable. So this is our initial ACME estimate, and here is when rho touches the zero line, and that is I think negative zero point 0.6 or 5.5 something. So it's not too unstable, but it's definitely not as stable as this one. And also the estimate is a bit lesser, but it is telling us that over the years the acme is getting less stronger, as much as we were able to see in the first model. So this is the model for cognition in longitudinal sense. And the first model is when we have childhood brain state as mediator and the adult cognition as outcome. So the ACME estimate for this one is between negative zero point 0.4 to negative zero point 0.5. ADE is slightly on the positive side, but because it was not significant, so we cannot conclude anything from it. However, the sensitivity analysis is the most robust out of all models, and here you can see that there is no zero on ACME axis, and it never touches zero for whatever value of rho. It's always the acme is always there. It might change its strength, but it never changes its sign. So that shows a very stable reverse and results. Sorry. And then the final model. This is the variation, a slight variation of the last model from the previous slide, that the main mediator here is adult brain state and its effects on cognition, but we have a second mediator, and we want to include this as a post-treatment confounding factor, and we want to see how this changes the ECME when we include it as a confounder. And you can see that ECME becomes 0, it goes to 0, and what is telling us that the effects that we were able to see through adult brain state were actually are coming from the childhood brain state, and this is kind of a confounding factor that is affecting both of these. So basically this what this is telling us, that this path is more relevant than this path, and that's why we can say that changes in brain state caused by early childhood malnutrition are lifelong and not completely reversible without until we plan some interventions or something for it. And also we can predict those changes uh, or the cognitive scores or from the early life brain state. And this is the sensitivity plot. It's a different kind of sensitivity plot, but the sensitivity parameter is different, but you see pretty much same thing, that the acme estimate, because it's already 0, so it touches right away with the 0 line, and the results are not stable for this mediator. Thank you. That was my talk, and Noel would like to conclude the session. What we saw in this session that was that the as we know that EEG is quite cheap and portable, and it can be a very important biomarker in finding the effects of malnutrition. And if we can do an early detection, we can definitely use some intervention and treatments to improve the quality of life for the individuals who suffered from malnutrition. And as we already established that it is a huge population, a huge problem worldwide. So EEG can be an important biomarker, and what this specific studies tell us is that uh, of the changes in brain state are set at school age, at young life, due to one episode of malnutrition, and that affects the quality of life for the individuals throughout their life until we do or plan some kind of interventions and improve their cognitive health. And that would be all for today's session. I'll thank you and also thank my speakers for the session. And if you have any queries or questions, you can ask us during the live question answer session in the IOP conference date, as well as you can send us messages on IOP platform for your queries, and then we can have a discussion. Thank you.